Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 4th, 2025, just yesterday. The standout result is that an editing diffusion model, adapted for geometry, delivers over 35% gains on the FE2E benchmark, and even beats the Depth Anything series, trained on 100 times more data. The paper is titled, From Editor to Dense Geometry Estimator. And as we'll see later, the implications for model training are quite significant. This paper argues editors are better bases than text-to-image generators for dense prediction, introducing consistent velocity training, logarithmic quantization, and cost-free joint depth and normal estimation. Alright, Figure 1 introduces FE2E as a compact editor-based model that predicts depth and surface normals from a single image and ranks highly despite limited training data. The top panels illustrate inputs, predicted normals, and predicted depth, which show clean object boundaries and smooth geometry. The bottom charts summarize average ranks across datasets, so shorter bars mean better overall performance. The yellow stars mark training data size, highlighting that strong results come with far fewer images. So, Figure 2 shows how the editor gets adapted into a deterministic geometry estimator that outputs depth and surface normals together. The key idea is consistent velocity, which means the model learns one-time independent motion in latent space, so inference becomes simple and stable. Logarithmic quantization maps raw depth into a log scale, which preserves relative accuracy for both near and far ranges. The pipeline reuses the unused right side of the latent layout to predict normals alongside depth without extra compute. So, Table 1 quantifies why logarithmic depth quantization is the right fit for BFloat16 training, because it keeps relative error nearly constant across near and far distances. Uniform scaling looks precise at long range but collapses at close range. Inverse, or disparity, excels up close but becomes unusable far away. Logarithmic achieves low abs-rel error at both ends, which makes fine-tuning stable without switching precision. Okay, Table 3 reports zero-shot surface normal estimation, which means predicting each pixel's 3D orientation without any task-specific training on the test sets. The table shows that FE2E delivers the best average rank while using roughly 71,000 training images. Results improve across both indoor and outdoor datasets because joint depth and normal supervision sharpens geometric detail. The consistent velocity training and log quantization likely help stability, so accuracy holds on challenging scenes. So, Table 2 shows that FE2E leads zero-shot depth estimation, which means predicting depth without task-specific fine-tuning on each test set. The method achieves the best average rank while using about 71,000 training images, so efficiency stands out. Results improve most on ETH3D and KITTI because consistent velocity training and joint supervision stabilize learning across scene types. The strong delta 1 accuracy alongside low absolute relative error indicates reliable depth at both near and far ranges. Annotations. Trigger text. Table 2 shows that bounding box 0.02, 0.18, 0.98, 0.95. Wrapping up, two takeaways stand out. Editing diffusion models make stronger, more stable foundations for dense geometry than text-to-image generators, and the trio of consistent velocity training, logarithmic depth quantization, and joint depth normal supervision delivers big zero-shot gains with little data. The broader implication is data-efficient geometry estimation at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.